Hello, I'm Hui Ling and I'm doing my PhD in the Aeronautics Department. I'm also a fellow of the Software Sustainability Institute, and today I'm going to demystify Git and provide practical advice on the basics of using Git. Welcome, brave adventurer, to Dungeons and Developers, where we'll be uncovering the secrets of Git. You awaken in a dimly lit tower of academia, scrolls scattered, datasets whispering in arcane tongues. You've been summoned to a research post, your quest to run code, manage chaos, and perhaps publish. But alas, your past is haunted by the cursed naming system of old. Script v1, script v2 final, script v2 final, please be last this time.py. In a moment of clarity or desperation, you invoke Git, the legendary tool of version control. You've forged a local repository using ancient incantations, and in the clouds above, you've conjured a remote GitHub repository. The two must now be bound. You gaze upon your code. Before you lies a scroll of arcane Git commands pulled from the internet. They shimmer with both promise and peril. Do you feel lost, wandering the forest of flags and options, or confident, ready to conquer the world of Git? Before you is the scroll of arcane Git commands. With these primal commands, you'll be able to shape the universe to your will, assuming the universe is your Git repository. I shall be your guide in unveiling and deciphering the contents of this arcane scroll. The first step whenever you work with Git on the command line is to run git status. It gives a quick overview about which branch we are on, what we are about to commit, which files might not be tracked, etc. This shows that all my files are currently unmodified. Now, I'm going to make a change to my README file by adding some text at the end. When running git status again, it'll show the changes which have not been staged for commit. As such, the status of my file is now modified. Running git diff shows the modifications that have been made to the tracked file. Adding the file through git add stages it. The file lifecycle is slightly different for an untracked file. So I'm going to create a new markdown file, and I'm going to call it Magical Superpowers. Running git status shows this file as being untracked. This differs from the README file, which shows the status as being modified. Now, I'm going to add all the files in my current directory to the staging area. Running git status again shows that both files have been added to the staging area, with the untracked file going from untracked directly to being staged. Armed with the knowledge of a file's lifecycle status, you, our brave adventurer in the vast realms of science, are now ready to take any file that crosses your path and add it to the Git repository. But a new question emerges from the shadows. What exactly should be added? Should I throw everything in to git add or not to git add? That is the question. There are some general rules of thumb. However, each project has different needs, so there aren't any hard and fast rules. With one exception. Never put any secrets or sensitive information into Git. Removing the file which held the secrets from Git will not remove it from the Git history. It needs to be purged from the history by rewriting it. This is a difficult and painful process, which I hope none of you will ever need to do. This is a cardinal rule that must never be broken and can become a serious security issue. Another important rule is that binaries should not be added to a Git repository. Git was designed to be a tool for source control, which means that it was built to look at textual changes. Thus, it can handle the presence of a binary file in the repository. However, it will hamper the performance of Git, making it slower and increasing the size of your repository. GitHub does place repository size limits, so this is worth keeping in mind. PDFs and PNGs are examples of files that Git has difficulty diffing. Generally, one should avoid adding these files to the repository as it affects the performance and bloats the repository. However, if your project is small, the reproduction of the files are impractical, the contents are tied to your source code, and accessing past versions are vital, and they change infrequently, then there may be a case for it. Large files, even text-based ones, fall into the same category. There are alternative solutions for such files that I will get into later in this presentation. Finally, files that are generated as part of the build process, like binaries for a compiled language or source files that are templated through a templating library, should not be added to the repository. These files can be recreated by executing the build process again. Thus, there is no need, and they should not be version controlled to keep the repository size to a minimum. Now that I've covered what should not go into Git, let's look at what should. Most importantly, your source code should be version controlled. That is something that everyone gets right off the bat. If your project is in Python, this would include the Python files, Jupyter notebooks, and anything else that's needed to run it, such as the pyproject.toml or a requirements.txt file. An often forgotten type of file to be source controlled are configuration files. These configuration files could be for your build, the running of the simulations, or tools being used as part of your development process. In short, what should be added to your Git repository is anything that is needed to reproduce your results. An astute listener may have noticed that I've now given you potentially conflicting guidelines. For instance, files that are not text-based shouldn't go into the Git repository. However, documentation is an important part of the source code. So should images present in the documentation go into source control? After all, an image can convey what words can't. If images are to be used as part of the documentation and would not change much, this is perfectly fine and is a good example of when one of these rules can be broken. Another conflicting rule of thumb is that large files should not be added to Git. However, I've mentioned that anything needed to reproduce your results should be added to Git. Thus, the case of what to do when large data files are needed to reproduce results comes up. This brings us to version control for data. Git is, in short, simply the wrong tool for the job. Data used in research is rarely invariant. Exceptions do exist, such as output from mechanical tests on a material. However, when raw data comes from an external source, aspects of it could change. For example, the file names or the expected structure of the data file. This would make the source code incompatible with the data, thereby threatening reproducibility. The goal of version controlling data is to capture the provenance of the result, that is, the precise subset and version of data a set of results originates from. The ability to track how raw data is processed, analyzed, and finally used in a paper is fundamental to the reproducibility of the work. Given its importance and that Git is not suitable for this purpose, what are the alternatives? Git large file storage handles large files by storing references to the file in the repository, but not the actual file itself. To work around Git's architecture, Git LFS creates a pointer file which acts as a reference to the actual file, which is stored somewhere else. GitHub manages this pointer file in your repository. When you clone the repository down, GitHub uses the pointer file as a map to find the large file for you. Git LFS is not the only available solution. LFS has the broadest target users and is the most immediately accessible. Anyone with a remote Git repository on GitHub or GitLab can use it. The main drawback is that it is a centralized solution, which means that large files are not distributed but stored on a remote server. As such, the Git hosting provider can place limits on aspects such as the maximum file size, how much storage is available, and the bandwidth usage. Personally, I use Git LFS for files that need to be in my repository and are not text-based. The first file is a netcdf file, which contains meteorological data. This is used by my test suite, so placing it in my repository makes the continuous integration workflow simpler. The next two files are images that have been used in my Journal of Open Source Software paper, thus it needs to be within my repository. DVC is targeted at AI and ML practitioners. DVC features distributed data management for collaborations, captures versions of data and models in Git commits, and has experiment management features out of the box. It guarantees reproducibility by consistently maintaining a combination of the input data, configuration, and the code that was initially used to run the experiment. Data-led is targeted at researchers working with data. Data-led is also a distributed data management platform which facilitates the collaboration on datasets and to easily publish the dataset. To summarize, DVC and data-led are more full-featured. If data is a large part of your work, then I highly recommend one of these platforms. If you're looking for a solution to deal with large files, then LFS is good enough. Now that you've mastered the art of handling large, unwieldy files, preserving their provenance to ensure their sacred rights of research reproducibility remain unbroken, we must now turn our attention to a new threat. Are there enchanted tools that can help us avoid accidentally adding these colossal files to our Git repository? Before us lies git ignore, a tool crafted to shield us from our own folly. This file specifies intentionally untracked files to ignore. For it to be effective, it must be placed in the root directory of your source files, where git init was invoked. It works by telling Git which files to ignore based on patterns specified within the file. When starting a new project, I typically use a git ignore template from GitHub. These are language specific, so for a Python project, I would use the python.gitignore. With your files in order and the wisdom of what to add to the Git repository etched into your mind, you stand at the threshold of the next great rite, the commit. Yet a familiar dread stirs within, the ancient fear of commitment. The staging area provides an opportunity to verify what you have added to it and what you want to commit to your local repository. Our first step is to run git status to check the state of our repository. We can see that README has been modified and some text has been added to the end of the file. Now, we are going to add these changes to the staging area. Running git diff again shows that there are no changes. This is because git diff only shows the unstaged changes. Since our only change has been staged, there are none. Passing git diff the staged flag now shows us the changes that we have placed in the staging area. Adding in another change into a different file, then running git diff will only show this new change. And git diff staged only shows the changes from the README. Now that I'm confident about the changes that are in the staging area, I can commit these changes with a meaningful message. There are 2 tips for keeping your progress safe. Firstly, commit early and often. It's better to have too many commits than too few. Once you have the commits, they can always be combined at a later date. Nothing can be done if there are too few commits. Secondly, if you're about to do something dangerous, fully commit beforehand. This guarantees that your code is safe. It is important to remember that once your changes have been committed, it is very hard to lose your code. Another tool to use with Git is pre-commit. This can be used to safeguard against mistakes from being committed to your repository. This tool is configured through a YAML file. This is an example file for a Python project. This configuration file specifies 3 commands are to be run on each commit. The first is to run rough as a linter. A linter is a static code analysis tool used to flag programming errors, bugs, stylistic errors, and suspicious constructs. It then proceeds to run rough as a formatter for the code. Finally, it invokes Pyrite to perform a static type checking on the Python code. If any of these steps fail, the commit will be blocked. The changes to rectify any issues that have been flagged need to be staged before they can be committed. It is also possible to invoke these before committing by running the pre-commit manually. I regularly run pre-commit when developing so that the various checks can pick out any issues that I might have missed on early on. We've now arrived at our final step, the push. Pushing your changes to remote can happen as frequently or infrequently as you please. Typically, I push my changes at the end of the day or after a significant set of changes that I don't want to risk losing if my laptop dies. The only aspect to keep in mind is that some operations become slightly more complex once the changes have been pushed to the remote repository. If you're using Git as a backup system, then you're less likely to run into this issue. It is only when you're working with more advanced features that this is worth keeping in mind. This scroll of arcane Git commands has finally been demystified. We started at the beginning when a developer makes a change to the files. This revealed the file status lifecycle. Once a developer is happy with a set of changes, the next step is to add the changes to the staging area. On the surface, this seems like a straightforward step. Upon deeper examination, the existential question of what should be added came up. in particular, how large files should not be added to a repository, and the alternative version control methods for large files and data. Moreover, tools like git ignore can be used to prevent the accidental adding of such files to the staging area. Committing is the final step to putting the changes that are in the staging area into the local repository. We've demonstrated how to verify that the changes we think we're committing are the changes that we want. Moreover, tools like pre-commit can be used to provide code quality assurances or to enforce a consistent formatting. Finally, when we have a commit or a set of commits that we are happy with, they can be pushed from the local repository to the remote repository. Any changes that have been made on the remote repository can be synced with the local through the fetch and pull commands. To conclude, Git has 3 magic words: add, commit, and push. We've seen how to use these commands, what the workflow is like, and what should and shouldn't go into a Git repository. In the event of emergency, all you need to do is commit and push. This is the second talk in the series. The next talk dives into how to write effective commit messages to craft a Git history that can be used for debugging and for understanding the code. Thank you, and I hope you enjoyed my presentation.